Welcome! Today we're diving into the fascinating world of the pH scale. Have you ever wondered why lemon juice tastes sour or why soap feels slippery? The answer lies in the pH scale, a simple yet powerful tool that helps us understand the acidity or basicity of substances. Whether you're mixing ingredients in your kitchen or conducting experiments in a lab, knowing about pH is essential. In this video, we'll explore what the pH scale is, how it works, and why it matters in everyday life. Let's start our journey by understanding the basics of this important scientific concept. The term pH stands for potential of hydrogen. It's a measure that tells us how acidic or basic a solution is. The pH scale ranges from 0 to 14, with 7 being neutral. Anything below 7 is considered acidic, while anything above 7 is basic, or alkaline. This scale is logarithmic, which means each step represents a tenfold change in acidity or basicity. For example, a solution with a pH of 4 is 10 times more acidic than one with a pH of 5. Understanding this scale helps us make sense of the chemical properties of everyday substances. Let's take a closer look at the pH scale itself. It's a numerical scale that runs from 0 to 14. At the center, pH 7 is neutral. Pure water is a classic example. Substances with a pH less than 7 are acidic, like vinegar or lemon juice. Those with a pH greater than 7 are basic, such as baking soda or soap. The further you move from 7, the stronger the acid or base. This scale is used in chemistry, biology, medicine, and even environmental science to assess the properties of solutions. Acids are substances that have a pH less than 7. They release hydrogen ions, H+, when dissolved in water. The lower the pH, the stronger the acid. For example, lemon juice has a pH around 2, making it quite acidic, while black coffee sits at about pH 5. Acids are common in foods, cleaning products, and even in our own stomachs, where gastric acid helps digest food. Understanding where acids fall on the pH scale helps us use them safely and effectively in daily life. On the other end of the spectrum, bases have a pH greater than 7. Bases release hydroxide ions, OH, in water. The higher the pH, the stronger the base. For instance, baking soda has a pH around 9, while household ammonia is even higher at about pH 11. Bases are found in cleaning products, antacids, and even in some foods. Knowing the pH of these substances helps us understand their uses and potential risks. Neutral substances have a pH of exactly 7. The most common example is pure water. Neutral solutions are neither acidic nor basic. This balance is important in many biological and chemical processes. For example, our blood is slightly basic, but it's very close to neutral, which is vital for our health. Maintaining neutrality in certain environments is crucial for life and for many industrial processes. You might wonder why pH is so important. The answer is that pH affects chemical reactions, biological functions, and even the taste and safety of our food and water. For example, plants need soil with the right pH to grow well, and fish require water with a specific pH range to survive. In medicine, pH levels in the body are closely monitored to ensure health. Understanding pH helps us make better choices in cooking, cleaning, gardening, and healthcare. The pH scale isn't just for scientists. It's all around us in daily life. When you use shampoo, brush your teeth, or clean your kitchen, you're interacting with substances that have specific pH values. Even swimming pools are carefully monitored for pH to keep the water safe and comfortable. By understanding pH, we can make smarter decisions about the products we use and the environments we create. How do we measure pH? There are several methods. The simplest is using pH paper or litmus paper, which changes color depending on the acidity or basicity of a solution. For more precise measurements, scientists use electronic pH meters. These devices can give accurate readings to 2 decimal places. Whether in a classroom or a laboratory, measuring pH is a fundamental skill for anyone working with chemicals. The litmus test is a classic way to check pH. Litmus paper comes in red and blue. Red litmus paper turns blue in a basic solution, while blue litmus paper turns red in an acidic solution. It's a quick and easy way to determine if a substance is acidic or basic, though it doesn't give an exact pH value. This method is widely used in classrooms and simple experiments. Besides litmus paper, there are other indicators that change color at different pH levels. Universal indicator is a mixture of dyes that shows a range of colors across the pH scale, from red for strong acids to purple for strong bases. These indicators are useful for getting a more detailed idea of a solution's pH, especially in educational settings and simple experiments. For more precise measurements, electronic pH meters are used. These devices have a probe that is dipped into the solution. The meter then displays the pH value digitally. pH meters are common in laboratories, water treatment plants, and even in food production. They provide accurate, reliable results and are essential for scientific research and industrial applications. At the molecular level, pH is all about the concentration of hydrogen ions, H+. In a solution, acids increase the concentration of H+ ions, while bases decrease it by producing hydroxide ions, OH. The pH value is calculated using the negative logarithm of the hydrogen ion concentration. This scientific approach allows us to quantify acidity and basicity in a precise way, making it easier to compare different substances. The pH scale is logarithmic, meaning each whole number change represents a tenfold difference in hydrogen ion concentration. For example, a solution with a pH of 3 is 10 times more acidic than one with a pH of 4, and 100 times more acidic than a pH of 5. This property makes the scale especially useful for comparing substances with very different acidities or basicities. Let's look at some common acidic substances. Lemon juice, vinegar, and soda are all acidic, with pH values ranging from 2 to 4. Even our stomach acid is highly acidic, with a pH around 1. These substances are part of our daily lives, and their acidity gives them their characteristic sour taste and cleaning power. Now, let's consider some basic substances. Baking soda, soap, and bleach are all basic, with pH values above 7. Baking soda is mildly basic at pH 9, while bleach is much stronger at pH 12. These substances are often used for cleaning and neutralizing acids. Their basicity gives them a slippery feel and the ability to break down grease and stains. Our bodies rely on tightly regulated pH levels to function properly. Blood, for example, has a pH around 7.4, which is slightly basic. Even small changes in blood pH can have serious health consequences. The stomach, on the other hand, is highly acidic to help digest food. The body uses various mechanisms to maintain the right pH in different organs and fluids. pH plays a crucial role in nature. Soil pH affects plant growth, while the pH of lakes and rivers impacts aquatic life. Acid rain, caused by pollution, can lower the pH of water bodies, harming fish and plants. Monitoring and managing pH in the environment is essential for maintaining healthy ecosystems. The pH of foods influences their taste, texture, and safety. For example, acidic foods like citrus fruits taste sour, while basic foods like egg whites taste bland. pH also affects food preservation. Pickling uses vinegar's acidity to prevent spoilage. Understanding pH helps chefs and food scientists create delicious and safe meals. Many cleaning products are either acidic or basic. Acidic cleaners remove mineral deposits and rust, while basic cleaners cut through grease and oils. Knowing the pH of a cleaner helps you choose the right product for the job and avoid damaging surfaces. Always handle strong acids and bases with care, as they can be corrosive. Farmers pay close attention to soil pH because it affects crop growth. Some plants prefer acidic soil, while others thrive in basic conditions. Soil pH influences nutrient availability and the health of beneficial microbes. Adjusting soil pH with lime or sulfur can improve yields and plant health. Maintaining the right pH in swimming pools is essential for comfort and safety. If the water is too acidic, it can irritate skin and eyes and corrode pool equipment. If it's too basic, it can cause scaling and reduce the effectiveness of disinfectants. Pool owners use pH test kits to keep the water balanced. Many industries rely on precise pH control. For example, in pharmaceuticals, the pH of solutions affects drug stability and effectiveness. In water treatment, pH is adjusted to prevent corrosion and ensure safe drinking water. Industrial processes often use automated systems to monitor and adjust pH continuously. Environmental scientists monitor pH to assess pollution and ecosystem health. Acid rain caused by industrial emissions can lower the pH of soil and water, harming plants and animals. Restoring pH balance is a key part of environmental protection effort. Regular monitoring helps detect problems early and guide conservation actions. Doctors and nurses often check pH levels in the body to diagnose and treat illnesses. For example, urine and blood tests can reveal imbalances that signal disease. Managing pH is critical in treating conditions like acidosis or alkalosis, where the body's pH drifts too far from normal. Medical professionals use pH as a vital sign of health. Cosmetic products are carefully formulated with specific pH values to protect skin and hair. Shampoos, soaps, and lotions are designed to match the natural pH of our bodies. Using products with the wrong pH can cause irritation or dryness. Understanding pH helps manufacturers create gentle, effective products. Corrosion is a chemical process that damages metals, often accelerated by acidic or basic environments. For example, acidic water can corrode pipes, while basic conditions can damage concrete. Monitoring and adjusting pH helps prevent costly damage to infrastructure and equipment. Fish and other aquatic organisms are sensitive to changes in pH. Most freshwater fish thrive in water with a pH between 6.5 and 8.5. If the water becomes too acidic or basic, it can harm or even kill aquatic life. Monitoring pH is essential for maintaining healthy aquariums and natural water bodies. Plants absorb nutrients best at certain pH levels. If the soil is too acidic or too basic, plants may struggle to grow. Gardeners test soil pH to ensure their plants get the nutrients they need. Adjusting soil pH can make a big difference in the health and productivity of gardens and farms. Water quality is closely linked to pH. Drinking water should have a pH between 6.5 and 8.5 for safety and taste. Water that's too acidic can leach metals from pipes, while basic water can cause scaling. Water treatment facilities constantly monitor and adjust pH to provide safe, clean water. Acid rain forms when pollutants like sulfur dioxide and nitrogen oxides mix with water vapor, creating acids. This lowers the pH of rainwater, which can damage forests, lakes, and buildings. Monitoring rainwater pH helps scientists track pollution and develop solutions to protect the environment. The world's oceans are becoming more acidic due to increased carbon dioxide in the atmosphere. This process, called ocean acidification, lowers the pH of seawater and threatens marine life, especially organisms with shells. Scientists monitor ocean pH to understand and address this global challenge. Industrial waste can alter the pH of rivers and lakes, harming wildlife and making water unsafe. Regulations require factories to treat waste and neutralize acids or bases before releasing it. Monitoring pH helps ensure compliance and protect the environment from pollution. Acids and bases react with each other in neutralization reactions, producing water and a salt. These reactions are important in chemistry, industry, and even in our bodies. For example, antacids neutralize stomach acid to relieve heartburn. Understanding pH helps us predict and control these reactions. Buffer solutions help maintain a stable pH even when acids or bases are added. They are crucial in biological systems, such as blood, where pH must stay within a narrow range. Buffers are also used in laboratories and industry to control reactions and processes. Healthy soil supports strong plant growth, and pH is a key factor. Soil that's too acidic or basic can limit nutrient availability and harm beneficial organisms. Farmers and gardeners test soil pH and add amendments to create the best conditions for crops and flowers. Brewers carefully monitor pH during beer and wine production. The right pH ensures proper fermentation, flavor, and stability. Too much acidity or basicity can spoil the taste or cause unwanted reactions. pH control is a key part of creating high-quality beverages. The pH of milk and dairy products affects their taste, texture, and shelf life. For example, yogurt and cheese are made by fermenting milk, which lowers the pH and creates a tangy flavor. Monitoring pH helps producers ensure consistent quality and safety. The pH in our mouths affects dental health. Acidic foods and drinks can lower mouth pH, leading to tooth decay and cavities. Saliva acts as a buffer, helping to neutralize acids and protect teeth. Good oral hygiene and a balanced diet help maintain a healthy pH in the mouth. The textile industry uses pH control in dyeing and finishing fabrics. The right pH ensures colors are vibrant and fabrics are soft. Incorrect pH can cause colors to fade or fabrics to weaken. Monitoring and adjusting pH is essential for producing high-quality textiles. Paper manufacturing relies on pH control to produce strong, high-quality paper. Acidic conditions can weaken paper fibers, while basic conditions can cause yellowing. By adjusting pH, manufacturers ensure paper is durable and long-lasting. In traditional photography, pH control is important in developing films and prints. The chemicals used must have the right pH to produce clear, lasting images. Incorrect pH can cause fading or discoloration. Even in the digital age, understanding pH is useful for preserving old photographs. Batteries use acidic or basic electrolytes to generate electricity. For example, car batteries contain sulfuric acid, while some household batteries use alkaline solutions. The pH of these electrolytes affects battery, performance, and safety. Proper handling and disposal are important to prevent harm. When cleaning up chemical spills, knowing the pH helps responders choose the right neutralizing agents. Acidic spills are treated with bases, and basic spills with acids. Quick, accurate pH testing is essential for safety and effective cleanup. To wrap up, the pH scale is a simple yet powerful tool for understanding the world around us. From the foods we eat to the water we drink, pH influences countless aspects of our lives. By learning how to measure and interpret pH, we gain valuable insights into chemistry, health, and the environment. Whether you're a student, a scientist, or just curious, understanding pH opens the door to a deeper appreciation of science and its impact on everyday life.